Hello and welcome to another session of Introduction to Astrophysical Fluids. In this session, we just continue our discussion from the previous session on the inviscid invariants for MHD fluids. Okay, so last time we discussed the conservation of mass, we discussed the subtle issues related to the conservation of linear momentum, and also finally we discussed very thoroughly the invariance or the conservation of the total energy. Now, as I just said, that unlike the ordinary hydrodynamic case, here we have three components of the total energy. One is the kinetic energy, another is the magnetic energy, the third one is the compressible thermodynamic energy, or sometimes we also say compressible potential type of energy. Okay. So, and we also saw that the form of that energy part, that compressible energy part, actually changes from, depending on the nature of the closure. Okay. Here in our cases, we just used two, we just showed that, two very simple closures. One was the isothermal closure, another was the polytropic closure. Okay. And then we also showed that basically the del T of the, or the ddt of the total energy basically boils down to a divergence of some quantity. Okay. And then also there is a point, that subtle point, that whether that divergence when gets integrated would vanish or not. For that we have to assure that at every point on the surface enclosing the volume of the flow, of the whole flow, is such that, or rather how to say that, at every point of the enclosing surface, okay, the dot product of certain quantities, let's say the velocity or the magnetic field, must vanish, okay, when it gets scalarly contracted with the surface area vector. Okay, so, or the surface vector. Okay, so that was all about the energy conservation. Now in this discussion we will discuss we will first introduce some quantities, new quantities, and then we also discuss their invariance. Okay, so the first one is the Cross-Helicity. Okay, so Cross-Helicity is nothing but a quantity whose density is given by the velocity, given by the scalar product of velocity and magnetic field. So if you just integrate V dot B over the whole space, you will get the total Cross-Helicity. Okay, and this is very important quantity in MHD because this somehow gives a measure of the interlinkedness of the velocity and the magnetic lines of force. Okay, so, or rather the streamlines and the magnetic lines of force. Okay, and people actually have succeeded to show that this quantity is an inviscid invariant in ideal MHD. Now, what exactly is the implication of that? Maybe we can discuss very briefly when we will discuss the turbulence in a plasma or in an MHD fluid. And there can be other implications as well. So, but in the scope of this course, it is just at least as of now, it will be just an information that Cross-Helicity is an inviscid invariant of ideal MHD. Okay, both compressible and incompressible. Okay, now my question to you is that can you show that? So in the last lecture I showed you very carefully step by step how to derive the energy conservation equation. So as you can easily understand, for to show Cross-Helicity conservation, you have to start with the equations like this: V dot B, and then you will have two terms, V dot del T B plus V dot del T V, correct? And then you have to use the governing equations to write the whole thing in such a manner that either that should be 0 or that should boil down to a global divergence term. Okay. Now, remember one very interesting thing, that when we discussed normal hydrodynamic fluids, okay, then some quantity we defined omega, which is the vorticity vector, you know, curl of V, and there actually we can also define another quantity which is V dot omega. And if you do that, this thing V dot omega is integrated over the whole space, you actually get another quantity which is called the kinetic helicity. Okay, so my question to you is, can you also show, can you actually also investigate whether kinetic helicity, so kinetic helicity, which looks like this, V dot omega d tau, is an inviscid invariant or not? Okay, and actually you will see that in case of normal MHD, kinetic helicity is no longer an inviscid invariant. Okay, so those two things you have to understand. Now finally we are talking about another quantity. This is the magnetic helicity. What is that? So magnetic helicity is that you take the scalar product with the magnetic field to its vector potential A, and then you take the volume integral. That will give you the total magnetic helicity. And this magnetic helicity topologically gives a measure of the twistedness and the knottedness of the magnetic field lines. Okay, so Moffat in the year 1970, he published a very very important work on magnetic helicity. Okay, and different type of topology depending on the magnetic helicity. So the question comes naturally, whether this quantity is an inviscid invariant for MHD. Well, the good news is yes, magnetic helicity is an inviscid invariant, and that we actually will investigate in step by step, thoroughly. Before doing this derivation, let me just mention one simple thing, is that you see that we have given a name helicity. Okay, and maybe in physics different type of context you can come across the word helicity. Okay, so helicity simply sometimes, so if you remember of for example in theoretical physics, sometimes helicity is given by the dot product of the angular momentum vector to the the linear momentum vector to the spin angular momentum vector. So this type of thing. So in any case, it is true that the linear momentum vector is a true vector and the spin angular momentum is a pseudo vector or an axial vector. Okay, so when true vector is contracted with a pseudo vector, okay, the scalar which we will get is a pseudo scalar. It's not a true scalar, right? Because by the change of the handedness of the coordinate system, this or how to say that, yeah, okay, I can say like this, by the action of the parity, okay, this pseudo scalar actually changes its sign, whereas a true scalar never changes its sign. For example, mass is a true scalar, okay, or the distance, okay, the modulus of a vector, that is a true scalar in general. But when you are talking about this type of scalar product, dot product of one polar vector and one pseudo vector, then simply you have this inversion of sign of that product under the parity, and then you can say that these things are known as like pseudo scalars. So all the helicities which we will talk in this case, they are actually all the helicities, okay, they are traditionally pseudoscalar in nature. Okay, so here you can simply see that V is a true vector, B is a pseudo vector, A is a true vector, B is a pseudo vector. As I said, kinetic helicity, V is a true vector, omega is a pseudo vector. And finally what I said, that this type of helicity, okay, they are giving in general topological views. So that means whether there are, so for example, for velocity you have streamlines, for magnetic field we have magnetic field lines. So helicity, I mean, sort of gives a measure of the knottedness or the interlinkedness of the different type of lines of force. I mean, of line between the lines of magnetic lines of force or the streamlines, or between magnetic lines of force and streamlines, that is given by some of the cross helicity. Okay, so this is quite a non-trivial subject. If you are interested, you can search over internet, and in the both in plasma turbulence and in normal fluid turbulence I have not yet introduced, but actually this is very interesting to see that helicity has a very important role. Okay, one thing is true, that magnetic helicity, whenever we talk about the for example the conservation of cross helicity or kinetic helicity, we somehow have to think that whether the system is compressible or incompressible, because we always have to consider this del V del T type of equation, and then the question of the compressibility of the fluid comes into play. But when we are talking about or talking of the invariance of the magnetic helicity, then simply you can easily see that magnetic helicity, but when we consider the conservation or the inviscid invariance of magnetic helicity, simply you can easily see that it does not depend on the velocity or the momentum evolution equation. So whether the fluid is compressible or not, it doesn't play a big role. I mean, actually it doesn't play any role here. So if we can show that this is an inviscid invariant for compressible MHD, it is also inviscid invariant for incompressible MHD, and vice versa, because I mean we don't need the fluid momentum evolution equation or the continuity equation. So in any case, so there is maybe one, and actually as you go through the proof you will see that we actually also do not need, in that sense, the divergence of V is equal to 0 property explicitly. So exactly that's why I thought to show this proof step by step, okay, so that you can understand different steps of the demonstration or the proof. So we are just trying to investigate the conservation of magnetic helicity, which is integration over hm d tau, where hm is nothing but a dot b. That is just a way of writing. I mean, I just took that symbol, and sometimes, so just following that, sometimes we also denote v dot b as hc, and we also denote v dot omega as hw, or sometimes we also say hk, kinetic helicity. There are different type of symbols. Okay, then what we have to do, we first have to derive, or I mean obtain the relations for this, right? And for that we need both del B del T and del A del T. So del B del T is given for ideal MHD, which is simply del B del T is equal to curl of V cross B. And from that, if you write B is equal to your curl of A, because that is the definition for the vector potential, curl of A is equal to B, then you can simply then write that curl of del A del T is equal to curl of V cross B. So del A del T will simply be equal to V cross B. Again, V cross B, you can write V cross curl of A, plus, because they are the curl of something curl of M is equal to curl of N simply says that M is equal to N plus some gradient, because if you take the curl of both sides, then these will vanish identically under a curl. So because curl of grad is 0, and that's why we have written del A del T is equal to V cross curl of A plus an arbitrary gradient of some scalar phi. Okay, and so this is a gauge basically. Okay, in case you don't know what gauge is, do not worry much. I mean, this is just, so for our current framework, this is an arbitrary quantity, which should come because we have from here to reach here, we have used the equality under a curl. Okay, so finally, del T of A dot B is nothing but del A del T dot B plus del B del T dot A. That we agree. And then del T of A dot B is nothing but U cross B plus gradient of psi dot B plus A dot curl of U cross B. Okay. Now so first of all, you will see that this part comes really from the del A del T part, and this term just comes from del B del T part. Okay, so this one I have taken here to contract into a divergence, because divergence of B is 0. So I can take B inside this and to write we can write divergence of psi times B plus, then you can see there are two things. One is you have one term U cross B dot B, which is 0, because in a scalar triple product, if two elements are equal minimum, then this is 0. So this is 0. So no problem with this term. Then we have this term. And this we can again use the identity that curl of M cross N is simply equal to divergence of M cross N, is equal to curl of M dot N minus curl of N dot M. So just using that identity, we can write this one as divergence of U cross B cross A plus curl of A dot U cross B. Now what is curl of A? Curl of A is again B. So B dot U cross B is 0. So finally I have this equation. So you see in the whole proof, so del T of A dot B is nothing but a divergence of a whole thing, where this thing inside this divergence, under this divergence, has no problem to be vanished at infinity, because B dot, either it will contain terms like B dot ds, or it will contain terms U dot ds. Okay, B dot ds or U dot ds. So in any case, you will see that this will ascertain you the inviscid invariance of the magnetic helicity. However, as I said, that we don't need any compressibility or incompressibility to show that. Okay, and as you have also remarked that here in this whole demonstration, we have also not used any closure property. That means P, whether this is a polytropic fluid, or this is a barotropic fluid, or this is an isothermal fluid, we don't worry. Okay, so that's why the conservation of magnetic helicity is a very robust property of a fluid, irrespective of its closure, irrespective of its compressibility. Okay, and so that's why this is very, very interesting for physicists who are doing also several type of thing like in space physics, including plasma turbulence, dynamo, several type of dynamo. So dynamo I have not yet introduced. So those two things, turbulence and dynamo, I will introduce very briefly in the last 2 weeks. Okay, so in the whole discussion till now, we have discussed the inviscid invariance of several variables. Okay, most of them are scalar in nature. Of course, mass and energy, they are true scalars in nature, and all the helicities, they are pseudo-scalar in nature. And also we discussed the only vector quantity and the conservation of this, that is the linear momentum, and we said that this is very subtle and this is not in general conserved due to the quantity like B tensorial B. Okay, so for all this thing in a nutshell, we actually saw that several physical quantities are conserved in ideal MHD, but this type of conservations are of prior importance in modeling different type of, or rather in explaining different phenomena in space and astrophysics. Okay, but the question is that whether the plasma, okay, or the MHD fluid which we are trying to describe, okay, in a certain specific astrophysical or space physical framework, what is the guarantee that the ideal MHD assumption is a good assumption? Because finally, if we can say that our fluid is such that this is of MHD type and all the viscous effects like the kinematic viscosity, the magnetic diffusivity, they are negligibly small or they are non-existing. Okay, well, non-existing is not possible, but at least they are negligibly small, then we can use this conservation of this helicity, energy, this type of thing, mass. But if this, of course, for mass we don't need viscosity, that's true, that is just a very normal thing. But for example, for magnetic helicity conservation, it's true that if we have eta, okay, if we have nu, for example, the kinematic viscosity, but no eta, then magnetic helicity is conserved, that's true. But if eta is there, the magnetic diffusivity, magnetic helicity is no longer conserved. Okay, so the question is that in practice, under which circumstances we can assume the MHD fluid which we are treating is an ideal one? Well, of course, the first like the answer or the first tendency of answer is that well, for the cases where the fluid has a very negligible viscosity, very negligible like magnetic diffusivity, and then you can say, well, this is a plasma, so if it has a very high conductivity, then maybe because if you remember the generalized Ohm's law, this is given by E plus V cross B. It's a very simplistic form, of course, after neglecting a lot of terms, this, and this is nothing but the conductivity of the plasma, right, of the fluid, sorry. So if sigma is tending to infinity, then this term is 0, and then basically your ideal MHD assumption is valid. E is equal to minus V cross B, right? Now the question is that, is it really necessary that always this should be very, very greater? Well, of course not. A smart answer is, well, this ratio should be very small with respect to these terms. Okay, then that is something very important. And that's exactly what is exploited in the framework of space and astrophysics. Okay, so now that's exactly what I said, that can we use the fact that because the conductivity is infinite, we can use ideal MHD? Not at all. So let us just look at the generalized Ohm's law, which should look like this. J by sigma is equal to E plus V cross B, where sigma is the conductivity, J is the current, E is the electric field, V is the fluid velocity, B is the magnetic field. Then E is equal to minus V cross B plus J by sigma. Now we take a very simple example where we actually use in practice ideal MHD, and we will see really that this one is very far from being infinity. Okay, so we just take the example of a magnetic loop in the active region of the sun. Okay, so if we take such a loop, then the magnetic field is very, very strong in that region, strong with respect to the the magnetic field what we actually observed in solar wind or something. So in solar wind at 1 astronomical unit, the magnetic field is of the order of 1 to 5 nanotesla. Now here this is 10 to the minus 2 Tesla. Well, this is quite high. Then the length scale, at which we are interested, is 10 to the power 6 meter. Okay, that is the typical size of the magnetic loops, for example. And U is 10 to the power 3 meter per second, and actually a bit larger than that even. Okay, so that is of the order of the kilometers per second. And sigma is 10 to the power 3, okay, ohm to the minus 1, meter to the minus 1, and that actually you can see that is high, but that is not infinitely large. Okay, 10 to the 3 is moderately large number. So J, which is B by mu 0 L, because it comes like 1 by mu 0 curl of B, so just by order analysis we can say this will be of the order of 10 to the minus 2 ampere per meter square. And then what happens, I can actually again change this to V and this also to V. Okay, so this is the velocity, okay, this, not U. And V cross B, just the order will simply be given by this times this, and that will be 10 volt per meter, roughly. We are just doing the order analysis. And J by sigma will be simply 10 to the minus 5 volt per meter, because J is this, okay, and sigma is this. Now you see, if J is not very small, let's say J is of the order of 10 ampere per meter square, then J by sigma will simply be 0.1. Okay, and then we cannot say that J by sigma ratio is negligibly small with respect to this one, because this is 10, this was 0.1, so it's just 1 by 100, right? But here when we say J by sigma is of the order of 10 to the minus 5, how does that come? 10 to the minus 3 and sigma is 10 to the 3. So this is 10 to the minus 2, this is 10 to the 3, so 10 to the minus 2 by 10 to the 3 is 10 to the minus 5, and this one is 10. So then finally, with respect to this one is very small. Okay, so there is a order 6. So 10 to the, this one is larger than this one by a factor of 10 to the 6. And that is why you can say that this term can actually be neglected with respect to this term, and so you can say E is practically is equal to minus V cross B. Okay, so your ideal MHD situation is retrieved. Okay, so that is something very interesting, that whenever doing some analytical relations and analytical like inferences, like some quantities are conserved, some quantities are not conserved, and so this type of inferences are very good, but on the other hand, it is also important to have a practical knowledge, so that you know the real order of magnitude of the parameters on the fields in several cases. Okay, for example, the magnetic field, the density. If you just do analytics using B, V, rho, P, T, without really knowing that whether what would be the practical values for V, V, rho, E, then actually this is just what? This is just playing a violin to a deaf person, right? You cannot enjoy the real essence of the subject. So the essential thing is to have a real knowledge, and at least for the, not the exact values, but at least the order of magnitudes of the variables of different situations, different in different frameworks of space and astrophysics. Okay, so here we just talked about the active region of the sun and the corresponding magnetic loops. Then another situation may be possible for the solar wind at 1 astronomical unit, at 10 astronomical unit, the plasma inside the solar corona, that is also possible. The plasma in a, I mean at the very large scale of a galaxy, that is possible, right? So all these things will only be meaningful if you know that, and actually you can yourself, you can understand that which model is much more appropriate than the other, only when you have a proper idea of the order of magnitudes of different quantities, different fluid variables, okay, in different situations. Okay, in the next lecture, in the next session, I will discuss a very small but interesting topic, that is that is an alternative formulation, an alternative writing style, okay, introduced by Elsasser in the year 1950, okay, to write the MHD equations, okay, when these equations are incompressible. So that's a small topic but quite interesting. So here for this invariance and this ideal MHD part, I am just ending here. So yeah, see you in the next session. Thank you.